Earth's new cosmic companion. So here's something that'll mess with your head a bit. Right now, as you're watching this video, Earth doesn't just have one moon circling around up there. We've actually got ourselves a second moon. Well, sort of. Before you rush outside with your telescope, thinking you're about to spot some massive celestial object hanging in the sky next to our familiar lunar companion, let me clarify what's actually going on here, because the reality is somehow even weirder than having a genuine second moon. The space rock in question is called 2025 PN7, and it was discovered in August 2025 by the Pan-STARRS telescope at Haleakala Observatory in Hawaii. This quasi-moon has likely been our close neighbor for about 60 years already, and it's planning to stick around until roughly 2083. That's another 60 years of cosmic companionship we're looking at. But here's where it gets interesting, and where we need to talk about what exactly a quasi-moon actually is, because calling 2025 PN7 a second moon is technically misleading, even though that's what everyone's been calling it. A quasi-moon doesn't actually orbit Earth like our real moon does. Instead, it orbits the sun on a path that's remarkably similar to Earth's orbit. From our perspective down here on the planet, it appears to be moving around us, but Earth and the quasi-moon are really both just dancing around the sun together. Think of it like this. Imagine you're on a running track, and there's another runner who's keeping pace with you, but running in a slightly different lane. To you, it looks like they're circling you, but really, you're both just going around the track at similar speeds. NASA has officially designated 2025 PN7 as a quasi-moon this week, which gives us scientific confirmation of what astronomers suspected when they first spotted it. The asteroid is roughly the size of a small office building, which sounds substantial until you realize that compared to our actual moon, this thing is about a quadrillion times less massive. That's a 1 with 15 zeros after it. So when people worry about this second moon affecting our tides or messing with Earth's gravity, you can relax. This cosmic pebble has virtually zero gravitational impact on our planet. The quasi-moon family. Now here's something that might surprise you even more. We actually have at least 6 other quasi-moons hanging around Earth. That's right, Earth is apparently quite the popular cosmic destination. These objects are all on similar orbits to Earth and remain reasonably stable over many years, though eventually their orbits will drift and they'll move away into the wider solar system. One of these quasi-moons might actually be a piece of our real moon that got blasted into space millions of years ago. The celebrity quasi-moon. The most extensively studied of Earth's quasi-moons goes by the Hawaiian name Kama'olelewa, which translates to an oscillating celestial object. Discovered in 2016 by Pan-STARRS in Hawaii, it immediately caught scientists' attention for reasons that go way beyond just its unusual orbit. Kama'olelewa measures approximately 165 feet in diameter and rotates incredibly rapidly, completing one full rotation every 28 minutes. For context, our moon takes 27 days to rotate once. This thing is spinning like a cosmic top. Its distance from Earth varies wildly, ranging from 9 million miles at its closest to 25 million miles at its farthest point, meaning even at its nearest approach, it's about 38 times farther from us than our moon. But distance and orbital mechanics aren't what make Kama'olelewa truly fascinating. What really got scientists excited was what happened when they pointed sophisticated spectroscopic equipment at this tiny asteroid and analyzed the light bouncing off its surface. The reflectance spectrum showed reddening beyond what's typically seen among asteroids in the inner solar system, indicative of a silicate-based composition. When scientists compared the spectrum to various material samples, they found something shocking. The best match was with rocks collected from the moon by Apollo 14 astronauts Alan Shepard and Edgar Mitchell. Specifically, the spectrum matched lunar samples from the Fra Mauro Formation in the lunar highlands. This quasi-satellite orbiting around with Earth might actually be a chunk of our actual moon. Let that sink in for a moment. Floating out there in space, keeping pace with Earth for potentially millions of years, is what appears to be a fragment of the moon itself. The Giordano-Bruno connection. Recent research suggests that Kama'olelewa was likely blasted away from the moon by an asteroid impact that occurred between 1 million and 10 million years ago. The impact that liberated this space rock also created one of the moon's most distinctive features, the Giordano-Bruno crater, which measures 13.7 miles wide. Giordano-Bruno is special among lunar craters because it's surprisingly young in geological terms. You can tell it's young because long light-colored rays still radiate from it, which is the signature of blast debris that gets covered over relatively quickly by subsequent smaller impacts. Scientists who study planetary geology can look at a crater and its surrounding ejecta pattern and essentially read it like a crime scene, piecing together when the impact occurred and how violent it was. The modeling suggests that the asteroid that struck the moon must have been about 1 mile wide to carve out the Giordano Bruno crater and send Kamo'olawa on its journey. If an asteroid that size hit Earth, it would release roughly the same amount of energy as detonating a 1 million megaton bomb. That's an absolutely catastrophic level of energy, powerful enough not just to excavate a massive crater, but to accelerate chunks of lunar material to escape velocity. Hit that subscribe button right now, because understanding how these cosmic mechanics work is key to understanding our place in this vast universe. The physics of lunar escape. For a piece of the moon to escape and eventually settle into a quasi-satellite orbit around Earth is actually an extraordinarily unlikely event. Charles Liu, astrophysicist at the American Museum of Natural History and collaborator with Neil deGrasse Tyson on One Universe, At Home in the Cosmos, has extensively studied orbital mechanics and gravitational dynamics throughout his career, particularly focusing on colliding galaxies and the star formation history of the universe. His work helps us understand the complex gravitational choreography required for something like Kamo'olawa to exist. When material gets ejected from the moon's surface through impact, more than 93% of launch conditions result in ejecta, either falling back to the lunar surface, hitting Earth, or escaping into heliocentric orbits similar to typical near-Earth asteroids. But in a small minority of cases, something special happens. About 6.6% of simulated launch conditions resulted in pathways leading to co-orbital states, including quasi-satellite orbits like Kamo'olawa's. The sweet spot involves material being launched at velocities just slightly above the moon's escape velocity, and preferably from the moon's trailing side. It's like throwing a baseball at exactly the right speed and angle so that it doesn't fall back down, doesn't escape into deep space, but instead enters this precise orbital configuration where it shadows Earth's path around the sun. Mini-moons, the short-term visitors. While quasi-moons like Kamo'olawa and 2025 PN7 stick around for decades or even centuries, Earth also occasionally captures what scientists call mini-moons. These are different beasts entirely. A mini-moon is an asteroid that Earth's gravity actually captures temporarily, causing it to genuinely orbit our planet for a brief period. The asteroid 2024 PT5 became a temporary mini-moon when it was captured by Earth's gravity on September 29, 2024, orbiting Earth for about 2 months before breaking free on November 25, 2024. The asteroid measured just 37 feet wide, making it over 300,000 times narrower than our actual moon. These mini-moon captures happen with some frequency, but we rarely see them because they're very small and very hard to detect. It's only been in recent years that our survey capability has reached the point where we can spot these tiny rocks as they temporarily join Earth's gravitational sphere of influence. Scientists have officially documented 2 prior short captures that last about a week, and 2 rarer long capture events. Bill Nye has explained how gravity acts as the cosmic glue holding our solar system together. Whether we're talking about planets orbiting the sun, moons orbiting planets, or these temporary mini-moon captures, it all comes down to the delicate balance between gravitational attraction and orbital velocity. When an asteroid approaches Earth with just the right speed and trajectory, our planet's gravity can temporarily snag it, creating these fleeting cosmic partnerships. The bigger picture, a dynamic solar system. What all of this tells us is that our solar system is far more dynamic than most people realize. We tend to think of space as this vast, empty void where things move in predictable, unchanging patterns. The reality is much more chaotic and interesting. Beyond Kamo'olawa and 2025 PN7, the known current quasi-satellites include 164,207 Cardia, 2006 FY35, 2014 OL 339, 2013 LX 28, 2020 PP1, and 2023 FW13. Each one is executing its own variation of this cosmic dance, appearing to orbit Earth while actually orbiting the Sun in paths that keep them relatively close to our planet. The same fundamental physics that governs how entire galaxies merge and interact also explains how a tiny asteroid can shadow Earth's orbit for decades. Understanding orbital dynamics and gravitational interactions isn't just about mapping space rocks near our planet. It's crucial for comprehending the ultimate fate of everything in the universe. The cosmic context. From quasi-moons to the Big Rip. This is where we need to talk about something that Neil deGrasse Tyson finds genuinely terrifying: the Big Rip. Tyson has spoken extensively about how the universe will end, referencing the Robert Frost poem with the lines about ending not with a bang, but with a whimper, not in fire, but in ice. As Tyson explains, we're living in an expanding universe that's cooling as it expands, and eventually all physical processes will cease as we approach absolute zero temperature. Trillions of years into the future, when all stars are gone and every process in every corner of the expanding universe has wound down, all parts of the cosmos will cool to the same temperature as the ever-cooling background. But before we get to that frozen end state, there's the Big Rip to consider. The Big Rip is tied to the accelerating expansion of the universe, which will eventually outstrip all gravitational forces currently holding things together. Think about what holds things together in our universe. Gravity binds galaxies, solar systems, and planets. Electromagnetic forces hold molecules together. But as the universe expands, dark energy drives this expansion faster and faster. The accelerating forces will continue to gain strength as we expand, because it's a property of the vacuum. And the bigger the universe is, the more vacuum we have. Eventually, this expansion will overcome even molecular bonds. It will rip molecules apart, then rip atoms apart, and finally, the very fabric of space and time itself will fall victim to this expansion. As Tyson describes it, the universe will try to stretch the very fabric and pixels of space-time itself, and when you can't stretch fabric anymore, it rips. The timeline for the Big Rip, in one hypothetical model, is around 22 billion years in the future. Long before that, our sun will have expanded into a red giant and consumed Earth, and the Milky Way will have collided with the Andromeda Galaxy. But for those keeping track of the universe's ultimate fate, the Big Rip represents a scenario where literally everything gets torn apart at the most fundamental level. The universe, a shooting gallery. This brings us back to Earth and our cosmic companions in a meaningful way. As Tyson points out, the solar system is basically a shooting gallery, with thousands of asteroids whose orbits cross Earth's orbit. These aren't just abstract objects floating harmlessly in space. They're out there, and it's not a problem provided we know where they are, how to track them, and how to deflect them. Understanding objects like quasi-moons and mini-moons isn't just an academic exercise. It's part of humanity's larger effort to map and comprehend the near-Earth environment. Every time we discover a new quasi-satellite or track a mini-moon, we're learning more about the population of small bodies that share space with us. Some of these objects, like Kama'oalewa, might be lunar fragments with stories stretching back millions of years. Others are captured asteroids that tell us about the composition and distribution of rocky material throughout the inner solar system. The predictable paths of quasi-moons make them ideal test subjects for space missions that need to practice delicate maneuvers near small bodies. China's space agency launched a mission to Kama'oalewa in 2025 to collect samples and return them to Earth, which would give us definitive proof of whether this quasi-satellite really is a chunk of lunar material, or if its spectral similarity to moon rocks is just a cosmic coincidence. The detective work continues. Every quasi-moon we discover and study adds another piece to the puzzle of how our solar system formed and evolved. These objects are like cosmic breadcrumbs, traces of ancient impacts and gravitational interactions that shaped the Earth-Moon system. The fact that we're only now developing the technology to detect and study these small bodies tells you something about how much we still have to learn. 2025, PN7 has a magnitude of about 26, which puts it far out of range of amateur telescopes. You need professional-grade equipment to even see it. Yet it's been shadowing Earth for 6 decades, and it'll continue to do so for another 6 decades. It's humbling to think about how many of these objects might have come and gone throughout Earth's history. Cosmic companions that danced with our planet for centuries or millennia before drifting away, completely unknown to the humans living below. The gravitational choreography that keeps Kama'oalewa in its quasi-satellite orbit is fundamentally the same physics that governs how galaxies interact and merge over cosmic timescales. We're living in a dynamic, evolving cosmos where nothing stays the same forever, where even something as seemingly permanent as Earth's orbit is part of a larger story of cosmic change and evolution. Looking forward. The next few decades will be exciting for quasi-moon research. We're getting better at detecting these objects, better at characterizing their orbits and compositions, and better at understanding how they fit into the broader picture of solar system dynamics. Sample return missions, like the one launched to Kamo Oalewa, could revolutionize our understanding of impact dynamics on the Moon and the distribution of lunar material throughout near-Earth space. The fact that Earth can temporarily capture these cosmic companions, that we can have quasi-moons shadow us for decades or centuries, that lunar fragments might be orbiting in sync with us millions of years after being blasted off the Moon's surface, all of this speaks to the incredible complexity and richness of the solar system we inhabit. We're not alone out here. We've never been alone. We've always had these small companions, these cosmic fellow travelers, sharing our journey around the sun. While we're studying these relatively nearby objects, we're also keeping in mind the broader cosmic context. The universe that gave us quasi-moons and mini-moons is the same universe that's expanding and cooling, the same universe that might eventually experience the Big Rip billions of years from now. If this deep dive into Earth's hidden cosmic companions has expanded your understanding of our dynamic solar system, then you need to subscribe to this channel right now. We're constantly exploring the mysteries of the ever-expanding cosmos, from the quasi-moons in our backyard to the ultimate fate of the universe itself. Hit that subscribe button and join us as we continue unraveling the secrets of space, one cosmic mystery at a time. The universe is vast, it's weird, and it's full of surprises, and we're here to explain every fascinating detail.